Hi, in this tutorial I'm going to talk about the Bayesian filter, but before going to that I'm going to explain a couple of formula and terms that we're going to need them later. So first I'm going to go through them. Well, the first thing that we need to know is obviously the Bayes rule, that probability of A given B is equal probability of A and B over the probability of B. That obviously we know. And the other thing is a total probability theorem that basically tells us, I will explain it by a Venn diagram. Suppose this is your random variable space, and this is the desired value for your random variable. For instance, you roll a dice and you're interested in the values that are less than, for instance, 3, and these are all the possible conditions between 1 and 6. So you can write the probability of x. You can discretize this space, not necessarily uniformly, but you can just discretize some cells, and you can see this area is equal to union of all these area together, which are mutually 2 by 2 exclusive. This one by this one, this one by this one. So you can write it as sigma or integral. It doesn't matter. If you're in continuous space, it's integral, and if you're discrete, sigma, but I will just put integral. Integral over probability of x and all these y's, like y1, y2, y3, y4. So union of this space and this part, and this part and this part. Okay. And as I said, you can just put a sigma here. And okay, so we will call this okay, you can use a Bayes rule here again. So you can for probability of x and y, you can write it down as probability of x is equal to sum of probability of x given y multiplied by p of y. I just use a Bayes rule here, multiply this guy by this guy. So this is number 1. Then there's a formula equation here that we're gonna use it often. It's probability of A given B and C. So conditional probability for B and C is equal to probability of B given A and C multiplied by probability of A given C over probability of B given C. So usually in the Bayes rule, you often have this term in the denominator, which is called normalizer, because we are interested this value to be a valid probability value between 0 and 1. And if you compute this term, it's usually not between 0 and 1, so you have to use a normalizer to make it between 0 and 1, and this is usually equal to sigma or sum over all these all the variables in the denominator. And this is usually a fixed term, and we usually put it here as a theta, or I don't know, some other symbol. So we don't take into account this one because it's a fixed value, it's not changing. Just have it in your mind. This is number 2. Number 3 is probability of A and B I will write the total probability for A and B. So I can introduce a new variable called, for instance, C, and just like I introduced the Y here for X. So it's a sigma, or doesn't matter, integral of probability of A, B over all these C. And what I can use the Bayes rule here. So I just write it down as is equal to sigma of probability of A given B and C multiplied by a probability of B and C. And again, I will use this, I will extend this term here, probability of A given B and Ci multiplied by probability of Ci given B multiplied by probability of B. So I just use the Bayes rule here, and we just call this 3, relative A given B and C. Okay, and the other thing that we need to know in head that is probability of A given B is equal to Bayes rule and B over the probability of B. I can write it down, probability of A and B from this term that I just calculated here. So sigma probability of A given B and C multiplied by probability of C given B multiplied by probability of B over the P of B. So I can get rid of these two. So I have probability of A given B is equal to sigma probability of A given B and C multiplied by probability of C given B. And I'll call this number 4. So these are 4 equations that we're gonna need soon. I'll just put it aside. Okay. Now we'll start with Markov assumption. And so imagine you have a network. Okay, let's say you got a robot that is in a particular state. Then you usually send a motion command, and you go to another state, and you have some sensors which do some measurements. So this is a very typical scenario for every robot, that you're in a state, motion command, sensor measurement, and continue. So imagine you're sending a motion command at time t-1, and you will go to state at time t-1. And it is important, afterwards you get into the state, you will do some measurements. These are all time t-1. Then according to the state that you have been and the motion command that you have taken, you will go to the next state at time t. So motion command plus the state that you have been, and afterwards you do some measurements. So as you can see from this graph, the measurement is only dependent on the state, and the state only depended on the previous state and the action that you have taken. So pay attention to this. Here's a t, xt, ut, and xt-1, and zt is only dependent on xt. Zt is not dependent on the zt minus 1, or it's not dependent on the xt minus 1 or ut minus 1. So these are the assumptions for this network that we have here. So I will just write it down so we know them. So probability of the measurement that we are making for all the state that we have visited earlier, and for all the measurement that we have done earlier, and all the motion commands that we have taken earlier, it's only dependent on the previous state. And you can see this guy only dependent on this guy. And it's very intuitive. Also, the state that we are in right now, given all the previous states, all the measurements that we have taken, and the all the motion commands that we have had before, it's only dependent on the previous state and the motion commands that we have taken. And you can see this guy is only dependent on this guy and this guy. So I will call them as 5 and 6. We're gonna need them soon. So we have 1, 2, 3, 4, 5, 6. Okay, so with this introduction and this background, we're ready to introduce the base filter. So it's a filter that it's a recursive filter that tries to relate the belief for the current state to the previous state. What does it mean? It means that we don't know our state exactly. All we know that the motion commands that we have sent earlier and the measurements after the getting to that particular state. For instance, you have a wheeled robot and you send a motion command to the wheel. Your robot moves and you will do some laser measurements, or you extract some shift feature, and then you will make another decision to send another motion command U and go to another state, and you will do the next measurement. So you always do the measurements and sending motion commands, and you're interested to know where is your state, or for instance, for localization, you want to know where are you in the world now. So the belief, we are interested to know the belief of being at that state xt according to or a given motion command at time 1, measurement at time 1, till motion command at time t, and measurement at time t. Remember from the Markov assumption that we had earlier that we first send the motion commands, we get into state, and then we'll do the measurements. So the indexes are t, t, t. Okay. Now we use the base rule here for this guy. I will call them, just to make the life easier, I will call this guy A, I will call these guys B, and these guys C. With the help of equation number 2, you can see probability of A given B and C. I will rewrite this formula as follows. Equation number 2. This is equal to probability of z at time t given xt, u1 z1 ut multiplied by probability of xt given u1 z1 till ut. So this is equation number 2. I'm just this is A and this is the C. This guy. And if you remember, here there's a probability of B given C, and as I said earlier, this is the denominator. This is a normalizer. This is usually something fixed number, because we are interested this guy to be a probability, so we sum it over all the possible values in the denominator. So this is usually a sigma or integral over all the c's, all the c variables that we have here, just to make it equal to 1, the sum for all of them. And we usually indicate it by some variable like eta or something like that, and we don't write it down again like probability of B and C, just eta. So in the next I will use the Markov property for our network. If you have a look in the formula number 5, the measurement, the time t, it's only dependent on the state, that time t. Z, it's only dependent on this guy. And here we have the same term exactly here. The time t, it's only dependent on this guy. So I will again write it down as probability of time t only dependent on, and it's nothing to do with the previous motion command or previous state, and it perfectly makes sense. It's really intuitive. Multiple by this guy here again, probability of xt given u1 z1 until ut. Okay, so I just use the equation number 5 to reach to this guy. Now from this term, I will apply the total probability for this term here. I will use the equation number 4. Probability of A given B is equal. And the total probability for conditional probability P of A given B. So I'm going to write it down as the probability of the T given measure time T is equal to, remember here you always introduce a new variable called C, and the variable that I'm gonna introduce here is the xt minus 1. So it's gonna be integral over xt given, you can see B and C, which is gonna be u1 z1 and the ut xt minus 1 multiple by probability of C given B, which is and as a C, the variable C that I introduce is xt minus 1, so probability of xt minus 1 given u1 z1 ut over, I hope I can fit it here, integral over all the xt minus 1. Okay, now I'm going to use the Markov property again, this time equation number 6. What does it say? It says probability of xt given previous state and the previous measurements and the previous motion commands, it's only dependent on the previous state and the motion commands that brought us to here. So equation number 6, I use equation number 6 here. for this part. Sorry, for this part. I use equation number 6. xt, it's only a given previous state and measurements and motion commands only dependent on the previous states and the motion command. So this guy is equal to xt minus 1 and ut multiplied by a probability of xt minus 1 given u1 z1 ut over all the xt minus 1. Okay, now if you have a look at the Markov graph here, and you can see that the previous state is only dependent on the it's nothing to do with the ut, because we are not still there, and it's only because if you look at the here xt minus 1 is nothing to do with the ut. It doesn't depend on that. So I can use a Markov property again and write it down as the probability of zt given xt divided by p of xt given xt minus 1 and ut multiplied by probability of xt minus 1 given u1 z1 to ut and ut minus 1 and zt minus 1, and it doesn't depend on the motion command at time t. You can see here this guy is not dependent on this guy over all d of xt minus 1. Okay, if you look carefully, as I said from the very beginning, it's a recursive filter. It tries to somehow relate the every state to the previous state, and you can see here we have xt minus 1 given previous measurements until the motion commands until the last measurements and motion command that we had, and this guy was what we have introduced here, but for the previous state. So this guy is the belief for the previous state, belief for xt minus 1. I'll just put it in blue. So I could successfully relate belief of xt somehow to my sensory data and my previous state. And it's perfectly makes sense. I mean, if it's very, very intuitive. Maybe it looks a bit confusing, but it says the belief that being in this state is equal to some fixed value here, p of zt given xt. What does it say? It's actually introduce our sensory data. For instance, our sensor. So okay, if we are really at the xt with the, for instance, if you're 2 meters away from a particular point, and we are using some laser scans with a reliability of, I don't know, 99%, this is correct. So this introduce our sense of reliability. Imagine you are really 2 meters away from something, and it's with a reliability of 99%. It's tell you that, okay, if you are really 2 meters away, with this chance you're that far away from that. And this term says, okay, the chance of moving from state xt with the motion command ut to this state multiplied by the chance of being in that state. Well, it's very simple. I mean, imagine you have a map like this, and you're here. You might have came from here, 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 here. So this is your xt. Okay, this is your xt, and this term here says, okay, the chance of being here multiplied by the chance of moving to here, because you may not exactly move from here to here or here to maybe you here belief of xt minus 1. This is your xt minus 1, and you plan to go to here, but you don't. But you ended up here or another state, because you never know. Maybe you, I don't know, your robot is I don't know, climbing a hill and it cannot, or it's over a hill and goes down much faster. So if your motion commands plans to reach you here, but you ended up instead of here, here, or here. So these are all of your xt minus 1, and this is your xt, and it's really, really intuitive, and it's pretty simple. That was the math behind it. Thank you.